Hey folks, welcome to Thames Off Grid. Today I want to go through some of the calculations and how the solar heater works. I think we've skipped all that through a lot of the videos. Let's back up a little bit. So first off, energy can neither be created nor destroyed. Ever heard that before? So we're trying to harvest solar radiation from the sun in the term of thermal energy. You know, photons come from the sun. Let's say they penetrate through glass like a car's window in the summertime. That's going to be in form of shortwave energy. It's coming through photons. Photons are getting absorbed by anything in the car. That's going to get radiated back out of the seats, the dash, the steering wheel, and everything else in the form of longer wave energy in terms of infrared. So think of the infrared, it's stuck behind the glass. So that's why the car is so hot. The longer wave waveforms cannot penetrate back through the glass like the short wave can, or short waveforms. So things heat up. Same concept here. We got solar radiation coming through glass, form of light, photons, absorption, and then we have infrared energy, longer wave, harder for it to pass back through the glass. So that's some heat and some energy that's getting created. So right now we got 48 degrees are coming in. We got about 86 degrees coming out, 87 degrees. So we're looking at, almost 40-degree delta T. So where my sensors are located, inlet venom in the back, top of the drip edge, as air crosses across the metal and comes down the drip edge. So capture that temperature. And then I've got the temperature in the back as it comes out of the drip edge and then out through the ducting. I have an anemometer back there. I'm looking at 844 feet per minute. That's going to come out to probably about 75, 73 cubic feet per minute. Why does all this matter? Well, let's do some math and let's go back to some of the basics. So here we go. And I wrote all this down so I wouldn't forget it. Some of the more important things to remember is to convert from BTU to watts, I divide by 3.412. So that's my BTU hour to watts conversion. What if I knew what my tons were and I was trying to convert to watts? I'm going to take my tons, multiply by 12,000 BTU per hour. Then I'm going to divide by 3.412. All right. And then we're going to have our watts when we start with tons. Now let's talk about specific heat load calculation. All right. I'm sorry. Specific heat load. Sensible heat load calculation, which in the sensible heat load calculation, you need to know the specific heat of air and you need to know the density of air. So one way to look at it is the mass times the specific heat times the density times the change in temperature, delta T, or we can use CFM, cubic feet per minute, times our delta T times 1.08, which is our specific heat times the density in another way without doing it in joules and kilograms and cubic meters. All right. The next thing that we would talk about is what we're going to do with this thing. All right. So right now, if it was 48 degrees in my kitchen in West Virginia, and I was bringing in 48-degree air, I could be pumping back out anywhere from 85 to 83 degree air. And this temperature sensor is a little bit right before the fan. So in my outlet duct, but before the fan, so its temperature is just barely different. But you can see the biggest delta T is our first pass heat exchange. Our second pass is picking up 12. All right. So 49 to 73, 59, 69, right? 20 and plus 4, so 24 plus the other 12. All right. Now let's talk about this. That kitchen in West Virginia, how long would it take and what are we doing here and how do we even calculate what you're doing? All right. So that kitchen is 15 feet long times 4 feet wide times a ceiling of 8 feet high. So 96 cubic feet. If I convert that to cubic meters, because I'm going to need that for another calculation, that's going to come out to 27.18 cubic meters because 1 cubic foot is 0.028 cubic meters. That's math. It can't be changed. Trust the science. Well-insulated room that has no furniture, has no countertop, has nothing. It's just a room with perfectly insulated walls and everything else. I could throw at it some calculations here that, hey, I can satisfy that space, 400 CFM per ton, and maybe only need 1 CFM per square foot. And this is me not just throwing some numbers out here, not applying any factors for lossage due to insulation values or lack thereof. So what's this thing putting out right now? That's the first thing you got to know. So we're going to use the sensible heat load calculation. So we know we're doing 70 CFM. We know what our constant is, 1.08. And we got about 40 degree delta T, or we had it a while ago. So that was 3,024 BTU per hour. And earlier I said divide that by 3.412. So 3,024 divided by 3.412, I've got 886 watts. So right now, 886 watts. What's the maximum this thing can put out? Oh, that's a good question. So think about this. I cannot capture any more than 1.36 kilowatt of the sun's energy per square meter, period. Perfect world, right? So whether it's a solar panel, a solar air heater, 1.36 kilowatt per square meter is all you're going to get. This is not a square meter, so I can't even get 1.36 kilowatts out of it. Why is it 2 pass? Because I noticed that it didn't seem like I could get the entire heat exchange over a single pass. What if I came up and back down? Could I get it all? So you can see the numbers here. I'm getting 12 more degrees by going back down. What if I had just come inside of them on the single pass? I don't know. So that's another test we'll do for another day in another box. But anyways, 886 out of less than a square meter, not bad. So now that we know what this can put out, now we can dig into our other equations. So if you know the size of the room, and we calculated it at 27.18 cubic meters, and we know that the specific heat of air is 1,000 joules per kilogram per degree Celsius, we know the density of air at 1.20 kilogram per cubic meter, and we know we want to get, let's say, 10 degrees Celsius change. Let's say I want to use this to heat the room 18 degrees, which is 10 degrees Celsius. I would need 3,288,117 joules. So, and I know what my power is. I know what my sensible heat load is in joules. I can derive how much time that would take to heat that space. So 3,228,116 joules divided by 886 watts is 370 seconds divided by 60 seconds in a minute, 6.17 minutes in a perfect world. So obviously, I'd say it's going to take more than 6.17 minutes. And let's say we're heating a space from 40 to 58, or maybe it's 50 and we're going to 68, 18 degrees. We're going to have to factor in some of the absorption rates of countertops and other things. So what I'm telling you, or what I've provided you today, are some of the calculations so that you can start to calculate what are you initially putting out. You're going to need an anemometer. I'm using one that's on the cord, and I've got the anemometer back here mounted in the duct. You're going to need some temperature readings. You need air temperature readings, not running around with an infrared temperature gun taking surface temperatures. You need probes with air passing through them to get air temperatures. You need that delta T. You've got your constant of 1.08. You can calculate how many BTUs per hour divided by 3412 and get your watts out of this. From your watts, you can calculate using your conversion of cubic feet to cubic meters, and you can use the specific heat of air and the density of air to calculate your joules. And from there, you can get your time and calculate it out. So while I've been talking, we're at 49. And our delta T is 24 across first pass. And then we're picking up another 12 on second pass. So I'm still pretty happy with it. Now, obviously, if I slow the air down slower than 70 CFM, we're going to get a different result. If I speed it up, we're going to get a different result. I encourage you to do all of those to find out what is going to get you the most BTU per hour or watts out of this. So play with the fan speed and see what your delta T's are and see what you get. So I hope you enjoyed learning the math behind all this as much as I did. It took a lot of research this morning, a lot of reading through things, and I've worked with kilowatt loading in my line of work and how that equates to CFM for decades. But equating it to joules and everything else today about how much time does it take to heat a space, That was something I had not done before. So I really enjoyed that. I hope you did too. So if you have any questions, post them in the comments. I'm trying to put the different videos into different playlists so they're easier to find. So if you're looking for something, just go into a specific playlist on a topic and you'll probably find what you're looking for until I can create a better way to find videos on the site. But really appreciate if you give it a thumbs up, a like, share, subscribe. But appreciate everybody. We're out of here.